Hello, my name is Rafael Sotelo from the University of Montevideo. I'm in the organizing committee of the IEEE Quantum Week. And we welcome to the session on resource optimization, number 2. We will have from 1 p.m. to 2:30. 3 papers will be presented, so 30 minutes each, please. So let's welcome our first presenter, Kaitao-san from Stony Brook University.
Hello, everyone.
Hello.
Hello, everyone. This is the afternoon of the last day. Some of my friends have already left, so thank you for the people who are still here. Today, I am presenting quantum sensor network algorithms for transmitter localization. This is a work from me, Kaitao Zhan, and my advisor, Himanshu Gupta. This presentation has 7 chapters, and I will start with the introduction and the motivation. The introduction begins with talking about the classical sensors versus the quantum sensors. Our world is surrounded by many classical sensors. For example, the wireless sensors. In our mobile phone, the wireless sensors are capable of sensing the received signal strength, or RSS, of the Wi-Fi signals, the cellular signals, and the Bluetooth signals. They can also sense more information, such as the channel state information. We all have image sensors that can sense the visible light. And there are also weather sensors deployed in the weather stations that can measure the temperature, pressure, rainfall, and wind. Now what about quantum sensors? What are them? I will give you some examples. The first example of a quantum sensor is called the single photon detector, that is capable of detecting a single photon. The second example is the quantum interferometer, where it can measure the tiniest change of phase of light. And they can also detect the very tiny gravitational waves. Some more examples are the MV center, where they have an MV spin that is very sensitive to the magnetic field. There are trapped ion sensors that is very sensitive to the electric field. And also last, there are RF-photonic sensors that is able to transduce the radio waves into the optics field and measure the optical quadrature displacement. Now I will introduce a network of sensors. In a sentence, it is very useful to have many sensors distributed geographically. This is a figure of one of my favorite applications called the Windy. What Windy do is that it collects weather data from all over the world. And what does it do? It runs the weather forecast models on the data collected from the weather sensors from around the world. So this is an example of predicting the trajectory of a hurricane. Now, what about a network of quantum sensors? In this figure, it is a physical experiment done by Professor Zhang and Zhuang when they were in Arizona. The idea is to utilize some quantum resources, such as the squeezed state of light and entangled input state. The key idea is to utilize the quantum resources such that the measurement is more accurate than classical sensors. And they have shown it in their physical experiments. Now, I will motivate my problem today of transmitter localization using a quantum sensor network, or QSN. In the past years, there are protocols that have been developed for the estimation of parameters using a quantum sensor network. People are interested in whether an entangled input can bring in an advantage comparing to non-entangled initial state. People are also interested in whether a global measurement can bring in an advantage with a local measurement. The parameters they are estimated are usually elementary physical parameters, such as the optical phase shift, the quadrature displacement, and also the electric fields and the magnetic fields. What is less explored is the usage of a quantum sensor network to estimate more complex physical phenomena as in many classical sensor network applications. One example is the location. Location has a huge impact in the wireless and mobile applications. Some more examples include weather data monitoring and health-related sensing. In this talk, I am focusing on the location. And I'll keep motivating using QSN for transmitter localization. In the past years, advances in quantum technologies has brought in efficient and sensitive quantum sensors for radio frequency sensing. This is two examples. The first one is the Rydberg atom-based spectrum analyzer, which is able to sense a very large range of spectrum from 0 to 20 gigahertz. So I am from the wireless community, and I know that sensing such a wide range of spectrum is very hard for classical sensors. Another example is the RF-photonic quantum sensors, as I mentioned before, that is able to estimate the amplitude and the phase of a signal more accurately than the classical counterparts. Now, I have finished the introduction and the motivation. In this slide, I will formally define the problem of transmitter localization. So let's look at this figure. To begin with, we generate an initial state that is distributed to a quantum sensor network. The quantum sensor network will interact with the transmitter, and then the evolved state will be sent to a centralized node for measurement and post-processing. Then we estimate the location of the transmitter. So we have a transmitter at an unknown location and a distributed set of sensors, which we assume are at known locations. The quantum sensor network is in an initial state of ket psi 0. The quantum sensor network will evolve into a final state, ket psi t prime, under the impact of a transmitter over a period of time, where the U-hat models the quantum sensing process. Now the final is the task. The task is to estimate the location of the transmitter based on the final state. So there's an unknown transmitter at xy, and the target is to estimate the location, which is, in this slide, x prime, y prime. Now I will talk about some related work in localization. I will discuss the related work in two axes. The first axis is the type of data, which can be classical or quantum. The second axis is the type of processor, which is also in classical and quantum. So there are 4 sections, and I will begin with the first section, CC, where you use classical wireless sensors applied with some classical machine learning algorithms, and then you do localization. In the past 2 decades, there are 100 papers in this topic, and I am referring to one of my previous work. The second section is the CQ, where you have a classical wireless sensor plus a quantum algorithm. You can also do localization. Here I am referring to a paper published in last year's QCE conference. The third section is the QCE section, where you have a quantum sensor and some classical processing, and you can do the RF classification. The fourth section is called the QQ, is where this paper stands. We're trying to use a quantum sensor with quantum processing and perform localization. The key idea of our paper is to pose the localization problem as a quantum state discrimination problem. Now, some more related work. First work is called the Discrete Outcome Quantum Sensor Network. It is a work from my collaborators, and this paper estimates discrete parameters compared to what most other papers do, which estimates the continuous parameters. Another related work is the Distributed Quantum Sensing Network, with geographically constrained measurement strategies. This paper focuses on the local measurement. In this work, we assume a global measurement, and we assume the existence of quantum communication because we need to send the state from the quantum sensors to a centralized node. This work is the first step of a quantum sensor network towards real-life application. Okay, now, I just finished the related work and the problem definition. Now I will talk about the quantum sensing model. The target here is to design an evolution unitary operator, UHAT, that models the impact of a signal to a quantum sensor as a function of distance. Now, for the impact on multiple sensors, we simply do a tensor product on the individual unitary operators. This is a figure that illustrates the intuition of the unitary operator. The intuition is that the closer the distance the transmitter is to the sensor, then the larger the impact the transmitter is to the sensor. Vice versa, the larger the distance the transmitter to the sensor, then the weaker the impact the transmitter to the sensor. So we assume at the sensor there is a Hamiltonian that is a function of E, where E is the electric field strength. And the electric field strength is naturally a function of distance, where the relation here is inverse. Based on this assumption, we are able to build a connection between the evolution unitary operator and the distance d. Now, in this slide, I will talk about the phase shift. In quantum sensing, the key quantity is the phase shift picked up by the quantum sensor due to the interaction with the signal. The time evolution unitary operator, U, due to a signal, can be expressed by this equation. It is the d to the I over h bar, and then we do an integration of the signal Hamiltonian. The signal Hamiltonian can be further expanded into this expression in colors. Note that here the gamma here is the coupling parameter that describes the coupling of the qubit to the signal. V is the signal itself, and the sigma z is the z-axis. The signal in blue can be further expanded by this sine wave, where E is the electric field strength, or the amplitude of the signal at the location of the quantum sensor. Now we rewrite this equation in a simpler form, and we have the phase shift here. The phase shift phi accumulated during the sensing time due to a signal can be expressed as this equation. So let's take a look at it. So everything here is constant except the electric field strength E. So gamma is the coupling constant which we can pick. The T prime is the sensing time, which in our simulation we set it as 1 millisecond. It is same for every sensors, so T prime is also can be looked upon as a constant. So the phase shift now is depending on the electric field strength, which is further depending on the distance between the transmitter and the sensor. For details, please refer to the paper. Now I'm halfway done. And now I will talk about the methodology, which is localization as quantum state discrimination. The key idea is to pose the transmitter localization problem as the well-studied quantum state discrimination problem, QSD. So what is QSD? QSD is, given a quantum state, ket phi, from a set of states with some prior, the task is to determine which state ket phi really is with some measurement. The key observation here is that different locations of transmitter will result in different final states. What does it mean? Here we have a grid of 4 times 4, cells, so there are 16 cells. Each cell is represented by the center point. So there are 16 center points. We assume the transmitters are at the center points only for now. So 16 center points will result in 16 different final states. The key idea here is that by determining the final state via QSD, we get the transmitter localization. I will reiterate the key idea. By determining the final state via quantum state discrimination, we get the transmitter location. With that, I will first talk about the basic one-level QSD method. This is a grid again. We have some sensors, and the transmitter is at one of the cells. What the QSD do is that it will discriminate against the 16 final states, and it will output the cell number, which is an index. And each cell number refers to the location of the transmitter. So the first step is that the QSN is in an initial state. Then we create a set of final states corresponding to the center of grid cells. So we have the set of final states. With that, we generate the POVM on the final states using pretty good measurement. The POVM here stands for the positive operator valued measure. In a sentence, this is the general form of the measurement. I will not go into the details. And the design of the POVM is not easy. And here we use a good way to generate the POVM, which we use the pretty good measurement. Again, I will not talk into details, but what pretty good measurement do is that it generates some measurement operators by giving a set of states and their priors. And here we assume the priors to be uniform. Now, finally, we localize the transmitter by a quantum state discrimination over the evolved final state using the POVM. So each individual quantum state discrimination gives you an output which could be erroneous. So we do the QSD repeatedly in a multi-shot manner, and we pick the most frequent outcome. So there are challenges of the one-level QSD. And the first one is that it has a high probability of error due to the potential of many states, because there could be many locations. The second challenge is that a global POVM measurement on a large number of qubits is hard. So we propose here a two-level QSD method where the coarse level determines the block, which is a sub-area of the grid. And then at the fine level, we determine the cell inside the block. So at each level, the POVM is on a fewer number of final states and fewer number of sensors. So it is kind of breaking a larger problem into a smaller problem. And this is a figure that illustrates the idea. This is again the 4x4 grid. But if you look at the thick dotted line, there is a 2x2 block. And each block is represented by a final state at the center of the block. So note that here the block centers does not overlap with the cell centers. But when we are applying the QSD will try to find the block center that is the closest to the cell center. So at the coarse level, the QSD will output a block number that refers to a block. And inside the block, we do a second fine level QSD, and it will give us the precise cell. But the QSD methods still have issues. It looks good in theory, but the POVM is hard to implement on the gate-based quantum machines. This is number one. And number two, the QSD method is inherently limited to discrete locations. So we have bring a solution here is to replace the POVM by the parameterized quantum circuits, and we learn the parameters via training. And in the end, we add a fully connected layer that can output in either discrete or the continuous space via different types of labels and loss function. A brief intro of the parameterized quantum circuits. The PQC works well on NISQ machines. It can be regarded as machine learning models with remarkable expressive power. And the common parameterized gates are the Rx, Ry, and Rz. And some a little bit more complex gate is the U3 gate and the control U3 gate. So we'll use this in our circuit. Our PQC-based localization has two parts. The first is the quantum part, which consists of blocks of U3 and control U3. Here, in each block, we have a layer of U3, and then followed by a layer of the control U3. In our circuit, we concatenate several blocks together. For the classical part, it first processes the measurement outcome, or the expected value of the Z measurement, followed by a neural network location predictor. The predictor has two variants. The first one is the classification variant, where each output neuron corresponds to a discrete location. For the regression variant, the output neurons they directly represent a coordinate, so that it is in the continuous space. And it can work in two levels too. You can always break a larger problem into smaller problems. Now I will talk about the evaluation. Again, the area is into a grid, and the transmitter signal's electric field model is expressed by this equation. So the electric field E is inverse of the D and proportional to square root 30 times P, where P is the power of the transmitter. In our simulations, we set the power as 0.1 microwatt, which is very small compared to the Wi-Fi access points we use in our daily lives. Now D is the distance between the transmitter and the sensor. And there's noise, because the wireless propagation will always have noise due to multipath effects and some other stuff. And here we assume it to be a zero mean Gaussian. For the sensor settings, we assume that the initial state is at a uniform superposition. The number of sensors ranges from 4, 8 to 16. And we assume the sensors are uniformly distributed. The transmitter location can either be anywhere in the grid, which is the continuous case, or only at the cell centers, which we call it the discrete case. The evaluation metric here, we use two kinds of metric. The first one is the average localization error in meters, and the second metric is the cell classification accuracy in percentage for the discrete case. We compare four algorithms: the one-level QSD, the two-level QSC, the one-level PQC, the parameterized quantum circuit, and the two-level PQC. We evaluate by simulation, and the circuits are implemented by the torch quantum. So here are the results. We have two observations. The PQC-based method is better than the QSD-based method. And also the two-level approach can improve the localization performance. So in this figure, the x-axis is the grid size, which we increase the grid size. The y-axis is the average localization error in meters. In this figure, the lower the line, the better. So the solid red line is the best one, and the solid red line is for the two-level PQC. If we compare the solid red line and the dashed red line, we can see that the two-level approach can improve the localization performance. And the figure on the right-hand side is for the discrete case, where the y-axis is changed to the cell classification accuracy. In this figure, the higher the line, the better. So that at top, we see that the solid red line is the best. And now is some discussion. The transmitter localization using quantum sensor network can achieve a meter level accuracy in an area of around 100 square meters. Note that this is not necessarily better than the classical wireless sensors yet. Classical wireless sensor networks can also achieve a similar performance. But I want to emphasize that in our simulation, the transmitter power is very small. And in this case, the classical sensors may not even detect the signals. So one point is that one advantage of the quantum sensor is that it is extremely sensitive. So effectively, the noise floor is a lot smaller. There are several ways to improve. One is we can try an entangled initial input. The other thing is to design a better or more realistic Hamiltonian. And also, of course, new localization algorithms. What cannot be improved is the noise in the radio signal itself, which always exists. And the hard thing is to have real quantum sensor testbed. So me from a CS department, we don't have real quantum sensors. So everything in this presentation only exists in my imagination. Now the conclusion. This is the first step of using a quantum sensor network in a real-world application, the localization of transmitters. We model the transmitter localization problem as a quantum state discrimination, and we make improvements via two ideas. The first idea is a two-level approach, and the second idea is using parameterized quantum circuits. And in the end, we do simulations we do extensive simulation. Now every code and result is on my GitHub account, and thank you for listening.
Thank you, Gustavo. Thank you very much. Very nice presentation, very clear. The steps. Thank you very much. So, is there any question?
Yeah, thank you for the talk. It's very nice. This is probably the only quantum sensing paper in this year's QCE, right? Sorry.
There is one poster on quantum radar.
Okay.
From Munich, and I'm very happy to see that poster, and I talked with that person a lot.
Okay. Okay. I think they are based on Radaver exam, right? Quantum radar.
That poster is a theoretical work, so I.
Okay. Yeah, never mind. I'm more interested in your work.
Okay.
So you assume the quantum process that the physical signal, the way the physical signal interacts with your quantum sensor is through a unitary.
Yes.
Time evolutional unitary.
Yeah.
And it depends on the distance. You have assumption,
yes.
right?
Yes.
Basically the signal strength. What is the real life example sensing apparatus that captures that your model captures? For example, in the light matter interaction, it's actually the frequency that dominates the frequency of the light that dominates this unitary. And what is the physical use case of your model?
That is actually something I want to investigate too.
Okay.
I understand that the real interaction between the signal and the sensor is a lot more complicated than the model I come up in this presentation. I do recognize that. And due to my limitation of knowledge, I can only design such a Hamiltonian that I can use.
I see. Yeah, that's okay. Another minor question is that when you design the POVM
Yeah.
at each quantum sensor,
Yeah.
what is the basis for this POVM that you measure? You need to quantize the energy level, right? Energy.
So for POVM, we use the pretty good measurement. So there is actually a detail on that. So this is the pretty good measurement that we use. Your question is on what basis is that, right?
The POVM.
For the pretty good measurement, I don't think you need a basis. For pretty good measurement, it gives you the measurement operator based on this equation. And if you look at this equation, it only depends on the states and the priors. So it is purely an analytical computation of the input states and the prior probabilities.
Okay.
And
okay. What is that rho?
Rho is the summation of the individual input states and the priors.
Also, you quantize all the in the gradient. For example, you have 16. So basically, you have 16 bases.
Yeah.
Okay. 16. All right. Okay. Thank you.
Thank you for your question. Any other question? No? So let's clap hands to speakers.
Thank you for the questions.
So our next speaker